All right, good day, everyone. Welcome to the week 13 office hours for applied machine learning. We'll begin 2 minutes after the hour, so please sit tight, wait for a couple more folks to join on, and we'll get going. And welcome back, everybody, from the break we had. All right, we're at 2 minutes past, so I think we are good to go. So let's begin. All right, so back here in week 13, we're going to review this module, which is basically our introduction to machine learning, right? And this is the portion of the course that follows on from all that foundational Python work we did over the first 12 weeks. And from this point forward, we're going to be looking at machine learning models and the techniques for building them and evaluating them. And this is good stuff, I think. You'll appreciate it. So first of all, right, in this week, Professor Paisley provided a nice introduction, or actually provided about 13 videos that we're going to discuss. I'll also go ahead and do some demos, I think, that illustrate some of the concepts of building regression models. And then finally, we'll take a look at the assignment. But in the first video, the professor was trying to introduce us to, just some of the jargon terminology and ways to look at the world of machine learning. And so in general, right, we're going to be trying to predict an output given a set of inputs, and building models to facilitate that process. And this is different than a lot of traditional programming, right? Where traditional programming, generally, you had a set of inputs and you programmed the rules in order to get to your outputs, right? In this case, you have inputs and outputs, and you're trying to learn the rules to go from input to output. It's quite a bit different and requires a different mindset, as we're going to be seeing over the next several weeks, right? And again, right, this is about discovery and uncovering info in data sets, getting larger and larger data sets, making them better and better, more and more refined and better suited to build these kinds of models. And there's all kinds of problems that can be solved with this, right? So in this part of the class, we're going to be looking at both supervised and unsupervised learning. The second half of the course of this next block of weeks are going to be devoted to unsupervised learning, but the first set are going to be devoted to supervised learning. Right? We'll talk about the distinction between these and the approaches that are used to build these kinds of models. So first, in the case of supervised machine learning, the idea here is that you will come equipped with a data set that has what's known as a labeled data set, right? Where it has a set of inputs and also has the correct answer for the outputs from that model, right? That's a labeled data set. So you can use supervised learning to build, both regression models and classification models, as you can see here. A regression model is generally a model that's trying to predict a real or continuous value from a set of data, whereas a classification model is trying to predict a label, right? So in the case of the regression model, take a peek at this little slide over here on the left, or this plot over here on the left. The idea is that that green curve, right, is intended to be the model that best predicts the value of those blue circular points, right? And we'll get into how that actually works and dig into the particulars of that. But that's essentially what a regression model is attempting to do, right? So the green curve in that case is the model, whereas those little circular points are the actual data, right? And the value along the y-axis is the labeled value for those particular points. Whereas for classification, this model here is trying to show, you're trying to learn that squiggly boundary, right, between the blue points and the yellow points. And then what you'd want to do then is use the function that was learned by that boundary to decide whether a point is blue or yellow based upon the input values that you're given. And this could be more than just two cases. This could actually generalize to any number of cases. There's techniques for that. And between these two, though, right, remember that regardless of whether you're building a regression model or a classification model, you're coming to do supervised learning, you need a labeled data set. Many times you don't have that, or many times you have some of that, and there are techniques to go and augment your data so that you have enough to produce a decent supervised model. We'll touch upon that later on in the course. Unsupervised machine learning is the opposite, essentially, right? You have a data set for which you have no labels, and you're trying to discover some sort of model on top of your data. This is once immensely powerful and a little bit counterintuitive and also a little bit mysterious, but there actually are techniques that are available to understand or learn patterns in data that are quite useful. If you explored some of the news aggregation sites that are out there on the web, for example, you might wonder how all these articles are finding their way to be grouped together by topic, health, sports, entertainment, whatever it might be. These unsupervised machine learning models actually do a fine job of learning these clusters within given sets of data. And then with a little bit of work from a data scientist, you could then go and decide and put a description on what those topics that are discovered are, right? And these techniques are surprisingly powerful, especially and in the realm of natural language processing. You can do quite a bit to learn about topics and learn actual vectors that represent the big bodies of text or data as just a series of numbers that end up being quite predictive of not only what the topic of a given document is, but also the similarity across documents. Documents that are similar to one another will tend to cluster together. And it's kind of, in a way, miraculous, but also quite simple. All right, so the professor then goes on to discuss this concept of data modeling, right? And for the rest of the lectures that occur in this module, he goes and refers to these blocks as sort of abstractions over major bits of the process of building machine learning models for regression analysis, right? So the notion here, right, is that, again, this is nomenclature just specific to this lecture, so you probably won't have much of a need to refer to blocks 1, 2, 3, and 4 outside of this lecture, but he does reference them extensively across the remaining videos in this, right? But the idea is that we want to, sort of understand, each of the parts of this flow chart that are necessary in order to go in and build these great models. We're going to go to this direct explore, right? So bringing data and a model together, right? Blocks 1 and 2, you then build or go through the process of inferring what the hidden variables are. I'll explain what that is in a little more detail in a couple minutes. Once you have that, then you can use your model to build predictions or to explore your data set further, right? If you're doing the supervised machine learning, you probably want to build predictions or probably want to predict from your model. If you're doing unsupervised learning, you probably want to use the clusters that are discovered or the groups that are discovered as a way to explore your model in a little more detail. And then there's a series of slides and lectures regarding an example that was explored in some detail, right? So the idea here is how can we build a model for a Gaussian distribution, right? So it's important to understand what the goal is here, right? So if you think about a Gaussian probability distribution, right, the shape that you see there in that plotted in that three-dimensional plot is really characterized by two different parameters, right? Those parameters are mu and sigma, right? Where mu represents the mean value and sigma represents the standard area or covariance. There's a couple names for it, right? But the idea is, it's how wide that curve is, right? And by using the formula that you can see next here with this squared exponential, right? This formula is used to allow you to make this plot in n-dimensional space, right? And what the idea here is, right, is that we want to figure out from observations of the data drawn from this distribution, how we could learn the parameters of the model. How can we learn what mu and sigma are, right, in order to produce that? So what the professor then goes on to do is to produce a thing called a probabilistic model, right? So the model itself, right, is parameterized by a vector called theta, right? So you're going to see this quite a bit in machine learning, where theta are the values that you want to learn in order to map X to some result Y, right? So in the case of the Gaussian distribution, right, the parameters we want to learn, the theta that we want to learn, are the vector essentially mu and sigma, right? And by the way, please don't be confused by the sigma that's used in this model, right? This is an uppercase sigma. It's not a summation, right? There's formulas that include that you will see that include both the sigma and summations. It's important to understand how to distinguish them, right? If it's a summation, it'll have the subscript and superscript annotations above and below the summation sigma, whereas if it's the parameter sigma, it's just that character that you see there, right? One of the things that underlies a lot of what's discussed here, right, is that we're presuming that our data are independent and identically distributed. What that means is we could take their probabilities and multiply them together in order to get their joint probability. If there's independence, then the probability of two things occurring is the probability of each occurring, multiplied by one another, right? So that's what that multiplied formula is showing there, right down below. And there's a trick that's used in building these kinds of models that you'll see over and over again, but instead of dealing with big, massive products, right, when you have many, many parameters, those products can get quite small and start to lead to numeric underflows, right? If you're multiplying a lot of small probabilities together, you can get a really, really small probability, right? But if you take the log of all those probabilities, that smooths it out so that the numbers are a little bit more numerically tractable and not quite so small. And for that matter, too, logs of products can be added, right, rather than multiplied. So that makes things much more numerically stable. Also, the professor discusses that this works because taking the logs are monotonic increasing along with the probability values. So if you take the logs of the values and then you optimize that, you're still optimizing the actual values themselves, right? And one thing that is also important to note, right, is that we're going to try to find what the argmax means here is we're going to try to find the theta that produces the best estimate of what our actual distribution is, right? And that's the maximum likelihood theta, right? And the argmax parameters are the ones that yield the maximum likelihood model, right? So one thing to note, right, if your model happens to be convex, which is that purplish model that you see down at the bottom, you could find the one and only optimal value for that. But if your model happens to be non-convex, you might end up in a relative maxima or a relative minima, right, for that value. That's a diagram showing up above with the two humps there, right? So that's a standard thing that we need to be careful of as we build machine learning models. And there's all kinds of heuristic tricks we could use to go and avoid the possibility of getting stuck in different relative maxima or minima. But the other thing that you'll note here is you'll see the presence of this upside down triangle, which represents the gradient, or sometimes it's called del. But that gradient value, right, is a way to get to the gradient's computed by taking the vector of the partial, of the partial derivatives of each of the constituent components of a vector, right, and forming a vector of those partials, right, and that gradient has the property that it points, it's a vector itself, right, and it points in the direction towards either the maxima or the minima of your function. So if you set that gradient equal to 0, you can actually find those maximum and minimum values. Sometimes this works quite well if you have a differentiable model and you know all the parameters of that model beforehand, right? So you can actually go and solve this, and then he actually goes through the process of solving the values for both mu and sigma, as you can see on this PowerPoint here, on this slide. And he derives, you can see the derivation here, right? But derives how to obtain those values given that numeric formula, right? But again, you're just taking a gradient, setting it equal to 0. So if you've done single variant calculus, right, then you're used to that. This is just done in the vector space. So I just got a comment in the chat from Joseph, says, what is the 2II looking parameter called? Hang on, let me go back. I'm not sure what you're referring to, Joseph. Let me go to the previous slide. So the previous, let me go back to the previous slide. Still not certain. Looks like a pi symbol. Oh, the pi symbol, I see. Let me, so Joseph was asking about, I believe this thing down at the bottom, it looks like an uppercase pi. It is indeed an uppercase pi, right? So that means the product, just like the uppercase sigma with, whoops, up in there. Just like the, so if you notice that pi has a I equals 1 subscripted below it and an n superscripted above it, those represent the, means the product of all those probabilities. So in this case, what we're trying to say, right, is that the probability, right, that we observed x1 through xn, right, given the parameters theta, is the product of the probability that I observed x1 times the probability I observed x2 times the probability I observed x3, right, all given theta, right? That's what that means, right? So, and the idea is we want to turn that big product or that big multiplication into a summation, and we do that by doing this log trick, right? We take the logarithm of everything, right? So that's what that means. No worries. Great. So this is the, again, the professor's derivation of the maximum likelihood estimate of the Gaussian mean. And, that's nice and useful. And the point of that is that using these kinds of models to build, to either maximize or minimize a function is really the essence of machine learning. And I'll explain, how that works. And I'll actually provide another example that illustrates this, right? So actually, let me go to that right now. So let's take a peek at this other PowerPoint. I'll send you a link to this PowerPoint, which is available from a public source. I think I've shared this before, though. This is from a talk that a friend of mine did at a session a few years ago. And let's see if I can motivate this well. All right, so imagine you had this set of data, right? And we're looking at, we have, for a set of diamonds, right, we have both their weight and carats, and we want to be able to build a model to predict the price based upon that weight, right? So it's a small data set, and you might be motivated to go, take, let's say, that weight, which is the input value in carats, right? And we want to go ahead and predict the price in dollars, let's say, or whatever currency, right? Plot them on the X and Y axes as shown here. When you plot those points, well, for any given point, first of all, right, you could see that, it's pretty simple, straightforward enough, right, to go ahead and, take any individual point. Now let's go and plot all these points out, right? And what you can see is that there's a sort of linear correlation, between these data, those two different parameters, right? So what we want to learn is a model that fits these data points best. And to do so, what we end up doing is, trying a couple lines that go through that data, and we want to pick the line that seems to be closest to those data points, right? So the idea then is once we have that line, we could then go ask the question, right, given any weight, right, what the price in dollars might be, right? So just go ask the line instead of, trying to go ahead and find a point that's nearby, right? And that model is about as good as, that sort of rectangular region around it that just got plotted. Think of that sort of as a confidence interval around your data, right? If that rectangle covers, right, most of the data points, or comes very close to covering them all, you have a really good model, right? But if you do that line maybe more horizontally or shifted it around, you might not get quite as close, right? So that's what machine learning is trying to do, right? And in this case, the way we describe this line, that requires two parameters, right? If you remember, some of the basic algebra, right, of drawing lines, the parameters that describe this line are one for the slope and one for the intercept, right, where this ends up crossing the y-axis, right? So we didn't know back earlier, right, before we drew that line, we didn't know what the slope or the intercept might be, right? We just went and, but machine learning will actually go and iteratively find those parameters for you, right? And that's, remember my point before about learning the rules rather than knowing the rules, right? So giving input, giving output, and we learn the rules. That's the essence of what we do with machine learning. So let me pop out of here. Go back to the other slide deck. All right, so now back in our current slide deck, the professor switches over to doing a linear regression model and uses the Old Faithful as the geyser in Yellowstone National Park in the US as the example case, where we're trying to predict how long we're going to need to wait for the next eruption of the geyser. And we want to do this given the duration of the last eruption from the geyser plus its W0, right? This W0 ends up corresponding to the offset or the intercept of this linear model across the y-axis. And that W1 parameter ends up corresponding to the slope of that line, right? So what we're seeing on this scatter plot is that there's a whole bunch of points that represent, given the current duration of the current eruption, right? What the waiting time is, right? That was associated until the next eruption. And this is, maybe 100 or so observations or so that are plotted here, right? And you can see that although they are scattered quite a bit, right, that they do tend to be, have this sort of linear trend to them, right? So, again, remember, right, W1 parameter that we're going to learn is the slope. W0 is the intercept, right? Intercept's also known as a bias or a shift or an offset, right? That's another way to hear that word characterized, and you'll hear that in deep learning as well, right? But this is a nice simple model. This can be extended though beyond just a two-variate case out to an n-variate case, right? So let's go from one-dimensional problem where given an eruption time, we want to predict the wait time. This next example that we touch upon tries to predict income given some measure of education and seniority, right? So, and again, they professor caveats, right? This is just only illustrating a correlation and not causation, right? Education doesn't necessarily cause you to have a change in your income, but they're correlated, right? And what the machine learning algorithms are trying to do in this case is learn three different parameters. W0 being, those three different parameters, by the way, describe the plane that's shown there in that yellowish color, right? So the red dots on the slide represent the individual observations, right, or the data points. And that yellowish plane is attempting to, again, be a three-dimensional extrapolation of the two-dimensional case that we saw drawn before, right, where we had a line going through a set of data mapping one-dimensional value, right, from one to another. In this case, we're trying to map two values to a third value, income, right? And so finding the plane that's closest to all those points is what the machine learning model algorithms will try to do. And that can go, the way that we actually measure how good a fit that plane is to our data points is done by, in this case, right, we're gonna look at this thing called the method of, I use the method of least squares, right? So what we do is, right, for each point, we measure the distance from that point down to the plane, right? So that is a measure of the error, right? Or another word for that is the loss, right? Where we are trying to determine just how closely we fit our data points. And the further away we are, the greater the loss is, right? So because the loss can have, a sign associated with it. It could be either above the plane or below the plane, positive or negative. Those could cancel out. So we square them in order to make sure that we preserve and have a positive value that we can just accumulate over time, right? So that's why we have squares, right? And then when we try to minimize the squared loss or squared distance from the plane, we get the least squares, right? So that's where that name comes from, right? So again, right, W0, W1, and W2 define that plane in space, right? And the loss function for that least squares plane is shown here in the lower right-hand side, where we know what the actual value is, right? That's the point in red. And we know what the plane is predicting. That's the value W0 plus the sum of the product of the input value, right? For, both X1 and X2, right? Seniority and education, let's say. Add those together, right? Add on the offset and the bias, subtract that from the actual value. We square these, right? So we don't have this sign cancellation issue. And we end up with an estimate of the loss, right? And what we can then do is what the really deep insider trick of machine learning is, right? Is we could take the gradient of that loss function and then use that as a way to go ahead and find the best plane, right? So for the case of the method of least squares in these simple cases, right, we can actually do this analytically and solve this equation without having to go and make guesses about how we should orient that plane. But in most n-dimensional cases, we actually have to take a guess at it and then slowly iterate our way down to what we think would be the minimum loss, right? And that's using a technique we'll discuss later on called gradient descent, but we're not there yet. We can actually find the point where the gradient equals 0, and that serves us quite well. All right, so beyond that, Joseph, I will share that slide deck that I mentioned that showed the illustration between the price and the weight of the diamonds, right? That was done by my friend Brandon Rohrer, with whom I used to work a while back, and he does these really great presentations introducing folks to data science. So regarding the so then beyond this, right? Sometimes a line itself, right, is not sufficient to describe your data. Sometimes a higher order polynomial was a better description for your data set. So imagine with those points in the scatter plot, those black dots, imagine trying to fit a line through that, right? You could get a line through a bunch of them maybe in that middle section, but it really doesn't do a good job of modeling those outliers that live on the extremes, right? Either towards -2 on the x-axis or out towards 2 or 3 on the x-axis, right? So the addition of some higher order terms could make your model a lot better, right? Now, this is still known as linear regression. And it's known as linear regression because the weights are linear, right? The linearity is referring to the W's, not to the input X's, right? So you could go and do linear regression on curves that have a higher order, that are higher order polynomial, right? And this is a matter where we start to stray out of the science and into the art of doing machine learning, where it's a matter of having some domain expertise and some experience in order to decide whether this is appropriate or not, and whether it's just something that is worthy of exploring. There actually are techniques that'll automatically or packages that'll automatically do this for you, but this is something that you might want to apply your skill and experience to decide whether to explore or whether these models are actually useful at these higher orders. Right now, this could be abused. You could go to a place where you have it too simple, right? Where we have, if you take a look, right, for setting the number of dimensions for the order of the polynomials we supply in, if we supplied a zero order polynomial, which is just a constant value, that's not going to do a good job of modeling our blue data points here, right? The first order, okay, right? But the ninth order polynomial would, while it would, be powerful enough to hit all those 10 points exactly, right? It's a little bit too, opinionated about how those data points actually should be modeled, and ends up not generalizing well. And again, this is something called the bias variance trade-off that you see in that we'll talk about in later lectures on machine learning, right? But the idea here, right, is you don't want this case here that's shown with n equal 9 with the ninth order polynomial modeling those 10 points. That's a severely overfit model, right? And whereas this model at n equal 3 seems to do a good job of hitting this sort of polynomial curve that has those two humps. And again, that's a standard third order polynomial. It generally has these kind of two humps to it. The second order has one, right? The third order has three, right? And it's a matter of just developing the right intuition for these kinds of things. You should also note too, right, that the models themselves don't only need to be confined to polynomials, right? They can also be confined to they could also be extended to include things like indicators or maybe other kinds of functions, right? So the professor does a nice job of generalizing that out beyond just the very basics of building linear or polynomial models. Great. So just checking to see if there's any questions in the QA. Looks like we're good. Okay. All right, so let me then start to take a wander into the week 13 assignment. Pop down here. So for week 13, right, there is a single Jupyter notebook that's used to cover, I think, some 8 questions or so that are assigned for your consideration and also for the exercise of programming. And it's going to, I'll walk you through it briefly here in a moment, but the idea is to explore building linear regression models using the method of least squares as a way to model a line through a series of points, right? The example that is done is, I think it's trying to predict a price of a home given the square footage of living space that house has the house has above ground, I think. And this is I think a well-known data set, and it has quite a few features and columns. And why don't we take a peek at that? So here's the Jupyter notebook, which is used for the assignment. So again, calculating the least squares weights, right? We're going to try to learn a series of, parameters, right, or weights that describe a function that'll take us from the input, which is all that information about the house, to the output, which is the sale price. Right? So again, so this is some discussion of using the notation that the professor, outlined in the class, right? So in this case, we're trying to learn a series of weights, right? And the least squares method here on these type of variables allow you to go ahead and do this analytically, right? So you can see the formula to go and compute that. But let's take a look at the data set itself. And so the data set is available for download right from, right from the Emeritus website. It just comes right down. It needs to appear in a subdirectory called data, right? So look for a file called train.csv, and we'll pull that in and take a peek at it. You can make a pandas data frame of it. You can see there's all kinds of possibilities, right, for columns that lead to that sale price, right? Remember, we're doing supervised learning, right? So supervised learning means, right, that we have a set of input features or variables or dimensions, right, that predict our label value, right? And we have a labeled value called the sale price, right? So what we want to do is learn some function that takes all of or some, right, of these columns and then produces that sale price value, right? And that's the notion of it, right? So digging further into the data set, right? So, or into the data frame, right? So, we could see the names of the various columns, right? So some things to note here, right? Some of these columns are numeric, right? So things like lot frontage or lot area, right? Year sold, months sold. Those things are numeric values that can be part of a linear formula pretty easily. You can imagine using some sort of weight coefficients to multiply times those values in order to produce a predicted sale price, right? But some of these values are not present or are not numeric or both, right? And so a lot could be shaped regularly or irregular, right? It could have, it could be hilly or level, right? These kinds of, we've actually touched upon this in the earlier part of the course, these are categorical variables that might actually be better encoded as a series of one-hot vectors in order to better build a regression model to predict this, right? So we'll touch upon that a little later on, right? So some of the basics here, right? So it's simply asking some questions about the basic exploration of the data. But this is a nice plot that illustrates the relationship, that's present in this data set between the living area and the sale price, right? So these are probably the most important variables that are part of this model, right? And you can see that as in generally, right, as the living area increases, right, the sale price of the home also increases. You can also see the data tend to get a little bit sparse as you get to the higher extremes of living area, right? And you get some really big variability, right, for the sale price of a home, up around 4,000 plus square feet or 5,000 some square feet, right? There's in the 4,000s, looks like there's 3 points, right? 2 of them represent a quite high sale price, but there's a big swing down to a low sale price for that rather large home. And same for the 5,000 plus square foot home didn't sell at that high a price, right? So data tend to swing out a little bit too much here for these outliers, and that's actually addressed later on in here, right? So again, right, we will go take a peek at how these are correlated, and then we'll actually code up the linear regression model for least squares using the analytic formulas that were derived in the lectures and up above here, right? So you'll code that up, and eventually what you get down to is, and let me just run all the cells. let's see if I can get you that last model that I want you to look at. Yeah, this you should get to a point where you have a regression line going through that data set. And that regression line should be, somewhere right towards the middle of that big cluster of points, right? And when you get down to the bottom of this, what you'll note is that you've learned some the parameters of this model, right? And those parameters are these two values right here, the intercept and the coefficient. And if you think about that even a little more deeply, right, what you're basically saying here, right, is that we, this intercept means our line starts and crosses the y-axis at 13,454 or so, right, just a little bit. That's a base price, right? For our model will predict for a 0 square foot home, you would pay $13,454, right? And then for every square foot increase, right, you would add $110 or $111 to that price. So think about that. For a 1,000 square foot home, right, we would add $111,000, right? So 111 plus 13 is $124,000, right, for a 1,000 square foot home. And then for every additional 1,000 square feet, we'd add on another $111,000. So 124 for 2,000, that would be 235, I think. And, so you can see what this model actually leads itself to that kind of interpretation, right? So that's good and useful, right? More complex models are not so easily interpreted. And that's one of the major objections to some of the deep learning models that are present right now, is that it is kind of hard to interpret them. And when we touch upon the unsupervised machine learning models later on in the second half of this course, or the last quarter of the course, right, you will see, right, that a lot of we're going to learn characteristics of these clusters, right, that are not so easily interpreted, right? So it takes a little more thinking on that. There's a lot of active research going on right now to try to make these deeper models more interpretable, right, or these unsupervised models more interpretable. But that's what we're going to be facing for this week. So there's a series of 8 questions in this notebook. The assertions and the grader doesn't seem to be especially fuzzy, which is good. So I think hopefully we won't have some of the issues that we encountered in the first half of the course with completing this assignment. But as always, right, please feel free to post to the forums, right? Both Ali and I will be actively monitoring them and trying to help you as questions come up. So now let's take a peek at just a quick mention of what's going on in week 14, and then I will await any further questions. All right, so week 14 gets into Riggs regression and Bayesian methods, right? The notion of Riggs regression is Riggs regression tries to handle the case where a lot of the data points that you receive are quite similar, right, or linearly dependent, I guess is the way to describe that, right? So when you have a lot of points that are, similar or collinear, right, mathematically, right, what ends up happening is they don't really span enough of the space, the model space, to give you as good a model as you might expect given the volume of data that you have, right? So Riggs regression attempts to go find a way to make up for that. I think it uses Lagrange multipliers underneath the hood to go ahead and make that all work. But that's something we'll take a peek at as a means to make our models better. Regularization is another technique that's used to prevent overfitting of models, right? And this this could be quite powerful, and some of the techniques used to regularize models can be quite surprising in some cases, right? In the case of deep neural nets, people actually will drop neurons out of different trials, right? That's called dropout. That's a way to prevent overfitting, but there's also L1 and L2 regularization, which basically I think attempts to penalize weights that and are parameters that end up being too large, right? So when you're learning, remember that theta vector, right, that we were trying to learn, right, of all the weights of the model, right? When any one of those weights gets really large, it's expressing essentially a very strong opinion about what the label value should be. And you can prove to yourself, or you can read the proofs that show that in those kinds of situations, uh, those kinds of parameters tend to overfit the training set. But when you go to test it or go and work against general data that the model's never seen before, um, those those types of those situations produce, those overfit kind of models, right? So the regularization tries to prevent that. L1 will try to take, cap off weights that are in a linear manner. L2 is a little even more aggressive than that and tries to, take a quadratic penalty against the weights, right? A second power penalty against the weights that are really high, right? So you'll just see these as techniques, and these are parameters to go and adjust. Are actually hyperparameters of your model to go ahead and outside of the params that you learn, and we'll actually learn the distinction between parameters and hyperparameters later on as well, right? But the weights that you learn for your model are the parameters, and then the other values that you adjust as you train and test your model are known as hyperparameters. They live outside of the model, right? And so the regularization variables tend to be characterized as hyperparameters for building a model. This again gets into some of the art of machine learning that you'll need to learn, and you'll grow to internalize and become part of your experience and toolbox as you become data scientists and machine learning experts. In addition, next week, we'll also cover Bayes rule and map inference, right? So map inference is, the maximization of the a prioris, right? Which is, again, remember Bayes rule, right? Is trying to allow you to express a degree of confidence about a given observation, given knowledge of probability distributions of the population from which that sample or that observation was drawn, right? So people picture, big bins full of different colored, ping pong balls, whatever, right? And you see a green one or a red one, you might conclude that this came from the first bin or the second bin based upon your knowledge of those distributions, right? So this is another critical bit of inference and intuition that you'll need to develop, right? Bayes' rule has been around for quite a while, and you can build some quite powerful models using it, right? So those will be touched upon in week 14. And with that, that's at the end of my slides for right now. So I will remain here for any further questions. And otherwise, I will see you on the forums, and look forward to having a great second half of the course with you.
John, you're on mute.
Whoops, can you hear me now? So hopefully you can hear me now. All right, thank you. The values in these x-axis, right, are attempting, x1, x2 through xn are these black dots, right? And the values, the x values are the values here along the x-axis trying to predict the y value, right? Again, we're building this model. If we just went with the x values to predict that y value, right, we would have a model that just used y equal x0 plus x1 or w0 plus w1x, right? That's a first order polynomial model. And what we could do is we could also square the values of these x's, and for that matter, cube the values of these x's, keep going on and on and on, right? As far out as that makes sense. And what ends up happening is, right, in the case of this kind of data distribution, it turns out, right, is two humps here, right, in our data, that this cubic model tends to predict it better, right? So that's using those, extending our inputs, right, beyond just the single value, but the single linear value, but also going to the quadratic and the cubic, right, allow us to go ahead and learn a couple additional parameters in our linear model that help us better relate x to y, right? So, the slide also, okay, so Joseph was saying the slide also includes the notion of these g's mapping, right, from one value to another, right? So the idea, right, remember, right, we could take these x's, right, our inputs, and we could cube them, we could square them, we could take it raised to the fourth power, right? That's nice. We can also do things like indicate, provide some sort of indicator, right? Where if the x value exceeds a certain threshold, we might give it a value of 1. And if it's below that threshold, we might give it a value of 0. Or we might decide to take the log of that. We might decide to exponentiate it, right? There's all kinds of things we could possibly do, right? So what those g functions are trying to do, Joseph, are trying to find a general way to indicate that there's some sort of mapping, right, between that input value and this additional value that's produced upon which the model is built, right? So it's just a generalized notation for doing this. And you're gonna, it's it's a little bit unpleasant, but we're gonna have to deal with a lot of this different kinds of notation in the world of machine learning and deep learning, only because it makes it easier for folks to go and express these higher level concepts when they write papers and do research on these kinds of things. So it's a little bit notation intensive, but please bear with it. That's all that it's really trying to do in that case. So this is going to be the first place where you start to touch upon the power of what you can do with these kinds of models. And hopefully you'll also start to get an intuition about what the limits are of these kinds of models, right? These models will definitely provide and have some good predictive value, but they can only go so far, right? They can give you a good degree of confidence in your prediction, and again, we actually have developed the mathematics that allow us to understand how confident we should be in our predictions, but the unlikely cases do occur, and the models do have limitations where they can't describe everything that they've observed, or they don't always generalize to the levels that they could, right? And there's also, right, these kinds of linear models that we're looking at here in the case of, this first case of looking at regression. We go so far, right? But we can go even further when we deal with nonlinearities, right? And actually deep learning later on beyond this course, right? If you go continue on and learn about deep learning allows you to build and learn nonlinear models, right? And that's why it's so powerful. One of the major things that's powerful about it, right? And that those kinds of nonlinearities allow you to build some really powerful models, like the ones that power all kinds of different sorts of natural language and machine vision type applications. All right, I'll remain muted until the top of the hour. Joseph asked, when we look at deep learning, that's a good question. I'll get that answered for you. And meanwhile, let me see if I can get the link to that particular slide deck that I was referring to. I think I found it here. The link to Brandon's deck and actually his whole presentation can be found here. And let me just slide this down. Again, here's Brandon's talk from a while back, from which I drew those slides that have the diamond weight to price model. Slides are available by clicking that link. And again, this is a good, I think I've referenced a session for it. It's certainly worth watching. It's a good way to come into the world of machine learning without having to dive into the math right away, which is good. It keeps you focused on what the purpose and goal of building machine learning models is as a data scientist. And it's a good grounding as we go and explore the math and the algorithms. And anyway, it's my pleasure to go and share all this with you. And I'm glad it's helpful, at least to some of you, so I appreciate it. And all right, well, I think we're near the top of the hour now, and I think we've covered this week's session pretty well. So I will look forward to seeing you all on the forums and having these next block of weeks together as we go and dig into building these models. It's going to be a lot of fun, and hopefully you'll find it to be both enjoyable and challenging and a great opportunity to grow. Thank you.